All right, we'll get started. We have a lot of material to cover because we're actually going to sort of formalize a process to solve for fault currents using a lot of the stuff we've done already. So using a load flow and then using a Y bus, we actually can just calculate any fault current anywhere in the system, even if there isn't a current connection to ground, essentially. So we're going to simplify things a little bit. So we're going to get rid of our pi equivalent and just include a series reactance. It's not going to hurt us too much. You certainly could include it. It just complicates building your Y bus, right? So that's the only thing that we say with item number one. Same thing with transformers. If we get rid of the equivalent circuit and just have it as a reactance, it simplifies things quite a bit. And transformers actually are a big source of limiting current on a system. So a lot of cases, you specify the impedance of a transformer based on how much you need to limit the current. Synchronous machines, we just introduced that the last actual class, which we're just going to model that as a constant voltage. That's our pre-fault voltage that we'll get from our load flow. And it's either going to be the sub-transient reactance if we're trying to calculate what the withstand ratings of the systems need to be. Transient reactance is what they're most likely going to interrupt, or a steady state, which if you're going to look at it long term. If you want to be the most conservative, use sub-transient. If you want to use the most realistic, use the transient. If you do have some induction motors, those are spinning loads, and they can contribute fault current, but generally they don't for very long periods of time because they don't have a magnetic field, right? Once the voltage on the terminals of an induction machine disappear, the magnetic fields collapse very rapidly. And even though it's spinning, there's no magnetic field, so you don't have any induced currents. So that's gone. If you want to be ultra conservative, yes, include them by treating them as a synchronous machine. And then the last one, if it's a non-spinning load, like battery storage, you just say that it trips offline. That's not going to store up enough energy for us to worry about any fault current contributions. All right, so let's take a look at a pretty simple example. We have a system here with a motor and a generator. And we have a transmission system with two transformers and a line between them. The delta Y and the Y delta do not matter to us at this point, but they will very short order where we actually have to keep track of those for ground faults. So we're going to assume that the generator has a 1.05 terminal voltage and supplies the motor that is consuming the equivalent of 100 MVA at a 0.95 lagging power factor. That is going to be a synchronous motor. We can treat it as an induction motor, but we're actually going to treat it as a synchronous motor because it's a fairly big motor, 100 MVA. You can see that I've got a bunch of synchronous reactances, one for the generator and one for the motor, and those are both sub-transient values. Now what we need to do is we need to convert our diagram to per unit, and unfortunately our transmission line is not provided in per unit. So we have to divide that by Z base, and our B base we're going to assume is 138 kV. Our S base is 100 MVA, and guess unless we know otherwise. So our line impedance works out to J.1. If we have a fault on the terminals, our diagram is going to look like this. We have synchronous generator with its sub-transient reactance. Then we have transformer 1, the transmission line, transformer 2, and then the motor. And then we have the actual equivalent voltage source for the motor. If we want to actually calculate, so remember the voltage that we have, this is 1.05 at an angle of 0 right there. So we actually need to calculate the generator voltage pre-fault and the motor voltage pre-fault, right? We need to see what those actual voltages are. So hopefully you see it's pretty easy. Our load is 100 MVA or 1 per unit at an angle of 18.2, which is going to allow us to calculate the current through this series circuit. That current works out to 0.95 at an angle of minus 18.2 in per unit. And so our generator voltage, our internal voltage, EA, really should call this EA double prime because those are subtransients, The actual magnitude of the voltage that the generator needs to create, if you will, is 1.103 at an angle of 7.1. We do the same thing for the motor, and we end up with 1.008 at an angle of minus 26.6. So at this point, we know this voltage here, we know this voltage here. We close the switch, and now we feed current into the fault. Once we've shorted the two systems, they're independent of each other, right? You have one system jumping all its current from the one generator, and then the same thing operating as the motor. Again, this is under fault conditions, so that motor is actually acting as a source for fault current. So that current works out to be J 9.09 per unit amps. I don't care so much about the fact that it's J 9.09. It has an angle. I really care about magnitude for fault current. So you'll hardly ever see angles associated with fault current. It's really magnitude because it's I squared times T. It's the magnitude of the current that a device experiences squared times the time period, and that's what indicates the heating and thereby damage. So I really only care that this is 9.09. That is the direct method to calculate fault current. It's just using standard circuit analysis that you've been doing all along. The problem is, it's a lot of work. If I have 50,000 buses and I want to look at all the different faults, I would have to do this 50,000 times. I'd have to do circuit analysis for each one. Yes, sir.
So when you're talking about faults, would it be like any location where fault is possible?
Well, that's the thing. Any location is possible for a fault, right? You have to assume that a fault can happen anywhere on your system. It is not a perfectly 100% reliable system. And because you have to isolate the fault, right? Imagine if your devices weren't rated enough to actually interrupt the fault, you'd keep feeding fault current for extended periods of time. Fires, damage, people would get hurt. That's part of the problem with inverter-based system because they have so little fault current. You could have a fault on a system and you can't even tell. Well, we're not going to use the direct method. Oh, yes, sir.
But then if you can you kind of like find the fault where there's higher current, let's say at generation, maybe there is higher current fault, then do it as if now.
How do you know that the fault current's going to be at the generator? What if it's someplace else? You remember, this system is all networked. You have generators all over the place. So you think, okay, a generator over here is going to have a lot of fault current. But what about a location that has 7 generators plus this generator feeding fault current? Is that possibly higher? You can't guarantee that that's the case, and you can't take chances here, right?
Yeah.
You can't say, well, I know that that has to be the highest fault current, so have a good life for everybody else. You're like, no, you got to prove that that's the case. So you all remember your circuit analysis classes way back, first year, second year? Were you taught superposition? Did you ever think, why would I do this? This is more work. This is silly, right? It's crazy. Why would I take them out one at a time and then add them all at the end of time? Why not just do them all at once? I have all these circuit analysis tools that I can do them all at once. Why bother doing superposition? It's for today. So I'll claim the responsibility for all your wasting your time doing superposition at the back of the day. It's because we're going to use the concept of superposition to drastically improve our efficiency of calculating fault currents over the direct method. Do you remember what superposition is? Take them all one at a time, then add them all up at the end. We're going to do the same thing here. But we're going to do the sneaky one, which is we're going to do all the other generators in the system, and do a load flow. That's going to tell us a pre-fault voltage at any bus location. Then the concept is superposition. We're going to put another voltage source in the opposite direction of the pre-fault voltage to force the terminal where the fault is going to have 0 volts. And the concept of superposition is you can do them all at once, or you can do a bunch at once and then add that last one in. And the current that I calculate is in fact going to be the fault current. That's what superposition allows us to do. So instead of doing the case one, which is the direct method for faulted condition, we're doing case two. Because before the fault has occurred, that doesn't exist. It's voltage source. If this is the voltage, if I calculate a V pre-fault of 1 per unit, if I stick a power supply over here and say that that's 1 per unit, there's no current that flows to that power supply, right? There's the same potential. They're at the exact same potential. So there's no current flow through that EF. But when I do superposition and take a power supply in the opposite direction, what is the voltage drop across plus to minus, minus to plus? They cancel each other out, right? They're in opposite directions. So by adding that additional power supply in the opposite direction of the pre-fault voltage, we actually get current. And that's how we're going to go ahead and do superposition. Questions for that? Because that's one of those ones, like I said, most people are like, why are we doing superposition? This is the reason why. Superposition allows us to add on this one source after we've analyzed our system. That's that one final one. And then we can calculate the actual current flow. That's going to be the actual current flow because of that additional voltage source. Yes, sir.
Because when you have to short circuit the supply, right?
I'm not short circuiting anything. A short circuit, what's the voltage drop across a short circuit?
Yeah.
Isn't that the same thing? When I have those two power supplies in opposite directions? Whether it's a short circuit or not, I get 0 volts. And if I use Ohm's law, V equals I times R, right? If I get 0 volts, I'm going to get all my current. So it's a short circuit. Exactly the same thing. That's the concept of superposition that we're using. So this is the pre-fault condition. Easy peasy. Just put a voltage source in there that matches the node voltage that you have. IF equals 0. Superposition says, all right, now I'm going to add a system and put a current source in the opposite direction. And you'll notice I turned off all the other systems, right? All the other values. And now look at my current. I get the current coming from generator 1, current from the motor, feeding into the fault. So now I got to use superposition to calculate my currents. So IG post the fault, right, is going to be the pre-fault current, what I calculated for superposition for the entire system, plus the delta IG, the addition of the pre-fault source in the opposite direction. And I could do the same thing for the motor. My actual fault current, that's the only one that had no pre-fault current because it was an open circuit, right? There was no connection. There was no reason for current to flow through the fault. It was at 0. So that's when I get my delta F. So let's do that same problem that we had before. Let me move this up out of the way. And let's see if we get the same answer. So pre-fault conditions, I got the two currents, right? We already calculate what the current needed to be. 0.952 at an angle of minus 18.2. Now I've got to go ahead and put in a power supply in the opposite direction, right? So you can see that what my current is going to be to the fault, 1.04 divided by 0.15, that's negative J7. And then I do the same thing for the motor post-fault, 1.04 at an angle of 0 divided by J. I got J2.1. My post-fault current equals negative J9.1. Isn't that what I had right here? Maybe I was a little more accurate, 9.09. Would you call that close enough to 9.1? I think that's close enough. That's the fault current, right? That shows the delta. Now, I also, and this is the nice thing, I actually can calculate the current after the fault has occurred, I can actually calculate it in the generator. 7.53 at an angle of minus 82.9. I didn't calculate the motor. Go ahead, B.
How do you find the free current?
The pre-current is here. Remember the load? This is the load, so that's the current right there. So why is this method a little bit better? Seems like it might be less work, although it's hard to tell. But what did I get for a current here that I didn't get in the previous case? I know what the generator current is after the fault occurs. Why is that important? Not exactly. Why is it important? I know what the fault current is from here. So we'll call it IFG. And I can calculate this current here, IFM, and then this is IF. Why is it good to know what IFG and IFM are? Maybe it's not. I think it is, though. Because all these generators, all these motors have protective devices on them saying, when there's a problem, go ahead and trip. But if I have some way of isolating that fault, whatever that way is, if I can isolate that fault before either of these devices open, then they can stay connected, can't they? They can continue to operate the motor and still keep the system alive and well. Right? So what I need to do, it's called selective coordination. Which means IFG, that magnitude of current, which is less, has got to trip after. So it has to be greater than the trip time associated with IF. Okay. And how do you do that? There's something called an inverse time characteristic. When you think of inverse time, do you mean go back in time? It's inverse time. The lower the current, the faster the time. Isn't that the inverse? The faster the current, or the faster, let me say, the lower the current, the faster, let me back up. The lower the current, the lower the time. Am I saying this correctly? If I have a little bit of current, then I have a lot of time. It takes a long time to trip. If I have a lot of current, it takes a little bit of time. So this current here is actually a ratio. It's divided by your pickup current. So this is the actual current. And this is my trip curve. This region over here is the trip region. This is no trip. And so as long as I have my devices coordinated, if this is the IF trip curve, and if this is the IFG or IFM, then I can go ahead and have this system continue to operate. This is one of the most important things we can do as a power systems engineer, because you're ensuring that this system can remain online after a fault has occurred. We've already said it's inevitable a fault is going to occur. It's going to happen. That's just how it is. But if you take the system out because a squirrel got crazy over in a substation in Orono, you take out all of New England, that's really bad. That means you're looking for a job. Because how many thousands of customers, millions of customers lost power because you didn't coordinate your system? And usually the feds will come and visit you and say, what is going on? That's what happened in Ohio back in 2003 or 2006. There was a lot of really pissed off people because they said, there's no way this should happen. A lot of legal stuff, a lot of lawyers. I told you about my experience at the nuclear power plant back in I think it was 2015, where there were some bad settings that the utility had set, and they ended up tripping off line Millstone power plant. And then they had to they had to declare an unusual event because within a pressurizer valve got stuck. That's a big problem to the nuclear facility. So I don't know what the legal stuff, that's all hush hush, but I'm sure there were settlements and all that stuff. Noah. Yes. Because it's not the it's not the independent variable. X-axis is always the independent variable, right? Y is always a dependent variable. I have no control over the fault current. I'm not adjusting anything, right? So the fault current is going to be what it's going to be. You just have to deal with it. The corresponding is here's how much time that fault current is going to be. So who's driving the bus? It's current. Most of the time you should draw your I primary to I pickup or I actual to I pickup on the x-axis and your time on the y if you want to draw them correctly. But some people get them backwards. And you can check. So there's a company called Schweitzer Engineering Labs. Anybody ever heard of them? I'll look at an SEL U3 curve. Hopefully that's legible. But these are the curves that they set. And if you look very closely over here, it says multiples of pickup. You know what multiples of pickup stands for? I actual divided by I pickup, right? Because if you're 3 times your pickup value, that means your actual current is 3 times the pickup value. That's all it is. But isn't this time? You can see it says time in seconds here. Hopefully that's legible. And this is multiple of pickups. And that's a unitless quantity. That's in per unit. You divide by your, in Schweitzer relays, you divide by your secondary current, but it's in amps. So the actual current, secondary current, divided by your secondary setting is how you trip. So that's why it's really useful to know those values. Super, super helpful to know that. So let's formalize it. Instead of actually doing anything crazy with voltage sources, let's just put in a current because we know what the current's going to be, right? It's the pre-fault voltage divided by the impedance of the system. And we'll see where the impedance comes in a minute. But that current, you just solve for it as, well, let's show it better here. I've got a new power source, right? And that current is going to go in all different directions. Is there a better way to figure out what that current is going to be seen by this generator? Is there a more effective way to do that? Any hints? Any guesses, I mean? What's that? Close. Rhymes with Thevenin and starts with a T. That a big enough hint? How about Thevenin? If I can solve for Thevenin equivalent, right? Those are equivalent to each other. So all I need is a Thevenin equivalent impedance seen by that additional source to calculate the fault current. Where do you think you're going to get the Thevenin equivalent impedance? And the diagonals of the Z bus are Z Thevenin seen at every single bus. So another huge advantage to building Y bus, because we actually can get the Thevenin equivalent impedances seen at all those buses. So all we need to do to solve for IF is take V pre-fault and divide by Z Thevenin, and that equals IF. So again, you can very quickly get that result. So here's our inverted Y bus, which is Z bus. And not only does it give us that fault current, but it also gives us the change in voltages throughout our system. Why are the changes in voltages more important for us? Because remember that generator and that motor, when they were feeding current? Well, after the fault occurs, you might want to know more what's happening between, okay, I have this motor and generator, but what if I have another line? How much current is going into the fault because of the connection between bus 2 and 72? I can solve for that by taking V at bus 72 minus V2 and divide that by my transfer impedance here, and I can actually get the current flow. Or, but I still need, I still need to get the delta V's, right? I still need to get those changes in voltages. So I've got to go ahead and get those change voltages as a result of the fault. So I'm just going to use my V equals Z bus I and get my delta V's. So here's kind of the process. We calculate our fault current by taking our pre-fault voltage at whatever bus the fault has occurred. You divide by your Thevenin equivalent impedance seen at that bus, or ZII out of your Z bus. And then you can go ahead and you can start calculating your updated voltages. For the bus, the fault at the bus, no big deal. We know that that's 0, right? That's easy peasy. The other voltages are all going to change. And so now, how do we apply this to any old system? So let's take a lot more complicated system than the previous 2-bus system. Let's go ahead and add this one. So we've got 4 actual physical buses, and we actually have some pseudo buses between the generators and the transformers, right? If you want to make it easier. We're going to assume that the system is initially unloaded just to make our calculations a little bit easier. And that's typically what we do when we do fault analysis, because the load currents are so much less than the fault currents, we can usually neglect them and get pretty good results. So here we added those pseudo buses, right? You can see how I put those pseudo buses in between there. I grabbed my subtransient reactances and put my diagram all as just a bunch of circuit elements. Now, you're certainly welcome. You can calculate putting a fault, at bus 2 by doing the direct method, but that's a lot of work for this system. So I'm not going to do that. I'm going to go ahead and use our superposition approach and go ahead and do that. So here's our pre-fault voltage case. We added that one supply and we've got that value in there. Now we're going to add in our negative V fault, and we're going to go ahead and get a fault current from bus 2 to ground. Okay, so I'm actually showing a neutral connection there, but we don't actually have to show it. I just wanted to show that, include that V, that connection to neutral, just to show that that's where the current is going to flow. All right, so let's build Y bus. So we have our Y bus, and now I just combine these systems. Remember, when we build Y bus, if we have impedances that are in series, we have to add them together first before inverting. So notice these are still impedances, not admittances, right? So I added them first. So it's J.22 inverted will give you negative J.4545. So now I have enough information. I'm going to go ahead and build my Y bus. You all are experts at building Y bus now, right? So here's my Y bus. Now I'm going to go ahead and put my fault on bus 2. So I'm going to show where my negative IF is shown right in position 2. This is my injected current, and this is using the superposition approach. Now I'm going to calculate my delta V's. So this is going to be Y bus. This is my delta V matrix, and this is my I matrix. So delta V is equal to Y bus inverse times my I injected. Okay, that's what I'm solving for right here. So now I can just pull out all the relevant stuff because I got a bunch of zeros everywhere except for at bus 2. So now I can see that the change in voltage at bus 1 is negative Z12 times the fault current. The fault, you don't even have to calculate this. Why is that? Why do I not even need to calculate this? Any guesses? Well, IF double prime, I solve for it by that equation there, right? So if I put that in here, I'm going to have negative VF equals negative VF. It's going to be just equal to 0, right? I'm not going to get any current there. So this is always going to be 0. Delta V3 is negative Z32 times IF double prime. And delta V4 is negative Z42 times IF double prime. And so now I just update my voltages, right? I've got those actual values. If you want to simplify, you can see that this here is the current, so I can stuff that into this equation, and then I can just use kind of a simpler approach. Z12 divided by Z22 times VF. That's just a ratio of the transfer impedance of the Thevenin equivalent impedance. You've got all the values there. Or I can substitute it in with matrices and then do it this way. And now I've got all the changes in voltages. Again, why is that important to me? Because if I go back to my original system and the fault is occurring here, I want to take out the breakers that are located near bus 2 to isolate bus 2. I'm going to have breakers most likely, if this is a decent sized power system. Most likely I'm going to have breakers at each end of the line and where the generators connect. So if the fault occurs here, these three had better, trip first, right? All these other ones had better weight. I don't want this breaker to trip before those other three breakers do. Anybody have an issue with me tripping that breaker? What's the problem if this breaker opens? We talked about it a little bit, but the system is less reliable, right? Because now I have kind of one line that's only energized at one side. So there's no power flow that can go through there. So that's useful. What else? What's the most important part? Well, maybe not the most important. It won't be damaged if you take those three closest breakers out of service. If everything trips pretty fast, you should be protecting your system from damage. Anybody want to guess as to what the other one, which is probably in some ways more important? I have a volunteer to come up and join me at the front of class. Come on up, Mason. Mason's a very nice guy. Thank you for coming up. For those of you in TV land, Mason, you can make your presence shown. Hi. So Mason has volunteered to do an assignment, right? That's why he's up here. All right. So there was a fault someplace, and this breaker opened, and that line is 40, let's say it's 50 miles long. It goes between Orrington and Winthrop or Windsor. Okay. Go find where the fault is. Nice seeing you. Have a good couple weeks. I will. You literally got to walk the whole line, right? He's going to go and walk the whole line because that breaker tripped. He doesn't want to close that breaker and say, oh, there's no problem. The breaker opened. Is he going to say close the breaker in? No, you don't know where. You don't know where. It didn't happen on that line, but he doesn't know that. His boss just said, you know what, you got to go shoot, you got to go walk the line. And then he wouldn't actually walk the line. He probably would most likely take an ATV. But if it's snowing and rain, that might not be so yes, right? Remember, these lines aren't what you think. These aren't, some of them have nice trails. They're not supposed to. They usually broke them off. But you don't have like nice ATVs. You know what everybody uses now? Drones. If you can. Got to be daytime, right? Because the drones, you can't fly them at night. You can't see that well. And the drone operator has to have enough light to be able to do it. So we just gave him essentially a task that he's going to be unhappy with. Thank you for volunteering. Yeah. Hey, where are you going? Grab your stuff and go, right? Oh, you want to? Kidding. But do you get the idea? You just made the job so much harder because now you've isolated a part of the system that has no failure whatsoever. But I definitely have to verify that that section of line is all healthy and good. And it's one of the scariest things. I can tell you when I was fairly new in my career, I had designed the electrical system for a power plant, and they had energized, it was a 150 MVA transformer, and it tripped just like that upon energization. Well, energization of a load, there was enough load through it. And it tripped on differential, which usually means there's a problem inside the generator. And the guy calls me up and said, hey, it just tripped on differential when we bumped the motor, but we don't have no power at the site. Can we turn it on? Can we energize the transformer? And I'm like, boy, that's a dangerous thing. When the transformer's got a failure inside, you're going to hit it again, more damage is going to occur. And I was like, I had to think about it. And I'm like, all right, we'll try it. It's a fast differential. It should trip again. And it stayed in. But this plant was in Houston and I was in Maine at the time. And so the answer was somebody had left a ground screw in. And they had currents going where they shouldn't have gone. But I had to be pretty comfortable because if the transformer, I told them to energize it again or allowed them to energize it again, and then it burns up, this was 20 something years ago. That was probably $2 million and an 8-month lead time. So that's, if I hadn't told them not, I would have had to go ahead and get oil tests done. I would have had to have do a bunch of tests. It would have been at least a week that they would have completely stopped the startup process. Because I said, nope, you can't energize it. But again, I had to use intelligence, and all because that one construction person, this is a startup engineer, really nice guy, but he argued with me about where to keep the ground screws. And my drawings, I said, put him here. And he says, no, I like him here. And I said, well, just pick one, but make sure you remove the other side. And he didn't. And that's the problem. No. What's that?
Why didn't you put the second time?
Because without getting into a lot of detail, you have a CT in here and you have a ground screw here and a ground screw here. And what was happening is there was supposed to be current going through a differential element here and a comparison on this side. And so what ended up happening is you had current going through here and then bypassing ground and then going back over here, and it wasn't going back through the other differential coil. So one said, hey, let's go ahead and operate it. And then the other coil, which was the restrain coil, didn't restrain it. So it said, yep, we got to go ahead and trip. Ground screws, literally, it's like a little copper screw, can kill you.
So why didn't they survive?
Because I told them to remove, because the load was so light. It wasn't enough to get the differential element to operate. It was at that point unloaded or very lightly unloaded, because they did a bump test on a 1,000 horsepower motor, and that pulled, 60% of the transformer's capacity, because when you bump it, it pulls a lot of power. But it was able to stay in. And then it was like, okay, why did it trip? And then I asked that guy that question, did you leave that screw in? And then he's like, well, maybe. He was the same guy that I told him to go lock out, tag out a breaker in the off position. He lock out, tagged it in the on position, almost killed somebody. So at that point, I said, I'm not helping you. You don't know how to work safely. So I kind of said, I'll answer questions, but I'm not going to direct crews.
Why did when you say do it again and then everything blow out? Will you have to pay for everything, or?
No, I probably wouldn't have had to pay for everything, but my company would probably say, have a nice life, Paul.
Oh,
You just did this. Somebody's getting sued.
yeah.
Yeah, I mean, most of the time, if you're doing things and you have like some reason behind it that's reasonable,
Yeah.
they'll generally like, hey, you did what you thought was the best thing to do at the time. But I would have told them, hey, I told them, I said, energize it, but make sure everybody's clear, because I don't know what's going to happen. So that means they took everybody that was working around the transformer because it was energized. And I said before they were working around it fine, but now it's like you get everybody out of there and energize it from a remote location so that you don't have you don't put personnel safety at risk. It's different. If somebody got injured, then yeah, you could get personally sued, but that you have to show real negligence, like you have no care for somebody's life. I did my due diligence to protect everybody, and I was pretty confident it was going to be okay because it had been running fine before. It's just that when they bumped the motor, that was the problem. That's when I said, okay, it's most likely a protection issue, but I wasn't sure. Good. Okay. So here's the process, right? Always, always, always step one, per unit. Take everything to per unit. Almost should do that before we do Y bus, because our Y bus tends to be in per unit. Step two, Do your Y bus calculation. Again, simplify it down. Just use series reactances. Invert your Y bus. Assume no load because that's close enough. And in some cases, if you want to do loading, you can, but it's kind of hard to do it. And most of the time, when you do fault analysis, when you're checking for fault current coordination, you almost always assume a flat pre-fault voltage. Because like Aspen One-Liner is a program I've used quite a bit. It really doesn't do load flows very well. So most of the time, you just assume a fixed pre-fault voltage. So we'll just set it at 1.03 is like the highest one you typically see. Then I calculate my fault current. And again, I'm going to pull this right out of my inverted Y bus matrix. That's a Thevenin equivalent impedance. You know how people used to calculate Thevenin equivalent impedances? Start series parallel combinations. If you had a power system with 1 million components, you conceivably would have to do 1 million components, but you made a lot of assumptions and simplifications at the time. But I've seen old calculations where they actually would, because to invert Y bus to get Z bus was very difficult up until like the 90s. So I saw calculations in the 80s where somebody was doing stuff by hand to calculate potential fault currents. Then you're going to go ahead and you're going to update all your bus voltages. And then now I can calculate any desired current through the transmission line. So I can check for coordination. That's really what I'm doing for step 7. If the fault is on transmission line AB or 1 to 17, then the current's going to be high enough. I got to isolate it like that. But if I've got other currents feeding it from another point, I've got to make sure that I'm going to wait. And you could say, and I know those guys in the back are going to start to harass me about something like, well, Paul, you're lying to us because line protection is used with distance relays. But the distance calculation is based on the amount of current that flows. So when the current is lower, your impedance is going to be higher, which means it's in a zone 2, which is a delayed element. Now they're like, maybe I shouldn't argue with them. Zone 2. What's that? Wyatt's ready to jump. And actually, the protection is even changing a little bit because they're using differential schemes on lines because fiber is so readily available that they're using you're using differential. You have certainty where the zone is. As long as the differential zone is set up reasonably well, you can go ahead and know for sure where the fault is, but you always have a backup because remember, I have to assume that a fault will occur. What if the communications device that would transmit or convert the fiber to whatever at your local station's gone? Then you have to have a backup scheme. So even though you have like more important lines like 345 kV lines are almost always what we call bulk power system requirements, which means you have to have 2 redundant channels and 2 redundant communication paths that are generally kind of separated from each other. And even with all that reliability, you still want to have some backup. So you would implement a standard step distance. All right, so let's do the same thing, right? So we're going to calculate the fault current at IF, and then we're going to look at some currents through the system. So we've already done our per phase equivalent for step 1. We built our Y bus for the system. We have that built here. Now we're going to invert and get Z bus. I don't know why I included it on here, other than what I should have done is just said these are Z Thevenins at each bus. We're going to assume a pre-fault voltage of 1 just to make the calculations easier. So now I'm going to calculate what the fault current is for a fault at bus 2. So I'm going to grab Z22, right? Because that's the Thevenin equivalent seen at bus 2. The fault current with a pre-fault voltage of 1 is 4.75 at an angle of -90. Yes, sir. I inverted Y bus to get Z bus.
But they just multiply the voltage times the Y bus, times the Y22.
No. No, because what I'm trying to get is the change in voltage. So V has to be equal to Z times I. I can't use Y. I have to invert it. I'm looking for V equals Z times I. If I was using Y bus, I would be calculating I, right? I already have I know what the fault current is. It's the pre-fault voltage divided by the Thevenin equivalent impedance seen by that bus. So I've got I, but I need to get the updated voltages. So that's why I need that equation right there. Yes, sir. Which one?
Right there, the one and blank with zero, VF over two.
Yep.
If you rearrange that, it would be VF times one over two, right?
ZF times what?
No, sorry, so VF, if you take it off the numerator.
Yep.
Just leave the one there, and be VF times one over two.
Yep.
That'd be the same as VF times one.
Ah, thank you. So for TV land, the question was, and tell me if I wrote this correctly, it's VF times 1 over Z22. Is that what you're asking?
Yes.
No.
Why not?
Are you telling me? Now I got to really pick on you guys. So if Y bus here is equal to Y22, do you mean Z bus, which I get from inverting Y bus, right, raised to the -1? Do you think Z22 is really just going to be Y22? Not when you invert the matrix, unless it's a purely diagonal matrix, right? With only diagonals and everything else is a 0. When you invert a matrix, yeah, the terms aren't 1 over, right? Everybody know how when you invert a matrix? To invert a matrix, tell me if I'm going too far. If I have y and I want to invert it, right? What I have to do is I have to multiply it by the identity matrix. And then eventually this has to look exactly like that. And that's what the inversion is, right? So you have to make it the identity matrix. So whatever I need to do, I need to make it the same. So yeah, it will not be the same unless your Z bus only has elements here and these are all zeros. That's the only time they'll be the same. But excellent question. No, they will not be the same. That's why I'm trying to talk about it as Z22, not the actual transfer admittance, but the Z bus inverter. Okay. And you can take a look, right? So over here, that's J.214, right? Let's go up to here. What is 1 over J 12.5 equal to? What is J? Just put, what is 12.5 inverted equal to? I can tell you what it's not equal to. It is not equal to 0.21.
0.08.
0.08. Not even close, is it? So why is it not the same? That's where you got to go all the way back to, you all took MAT 258, or some of you took MAT 258. Did they show you how to calculate the inverted matrix by hand? Did you do that? Okay, so that's the step that you need to do. It's like the method of cofactors and the adjoints and all that stuff. You know, we'll just take advantage of our calculator to do it. But yeah, it's not the same. But really, thank you guys for asking that question, because that's what everybody assumes. I can just invert it and go back. We just saw you can't do that. Okay. All right, so now we just update our voltages, our pre-fault voltages, and we're all 1 at an angle 0. And then look after the fault. The current is really high flowing through the system. That means we get voltage drops to our system. So it went from 1, 0.414, 0.372, 0.327. And now if I want to get the current transmitted through the transmission line between bus 1 and 2, I'm getting 2.07 amps, as opposed to the current, which is 4.753. So now what I've got to do is I'm going to get in the fault, I'm going to get 2.07 amps over here, right? I would then check the current over here to make sure that that current should be lower so that the devices over here don't trip faster than the devices over here, which they should. Because if you think about it, the current going through here includes the generator plus whatever current going through there. So we should have less current flowing through the line from bus 4 to bus 1. Wow, I got excited. I didn't think I was going to go that fast. Did I go too fast? But this is the heart of checking for coordination and power systems analysis. This is exactly what you need to be doing. And all those systems, all those power system programs, this is exactly what they do. You can't do a method more efficient than this. You can try, but it ain't going to work. Questions on this? Because I went a little bit faster than I was anticipating. I guess I got too excited. If you want to learn more about protection systems, talk to those two guys in the back. Just kidding. We're going to be doing EET422, which is where we do more with relays and protection systems. We'll be doing that more next semester, looking at coordination. So we assume that you know how to do load flow. We'll do symmetrical components over again, maybe a little bit of per unit, but then we'll very quickly talk about distance protection schemes, differential, overcurrent protection. There's even way more sophisticated than that. Volts per hertz protection, voltage protection, that type of stuff. But you notice how we focused on current. Any guesses as to why? That is by far the most common protection scheme you have. And it's the easiest one to do. Look at your house, right? You got a breaker in your breaker box that protects your system. So even at your house level, simple, cheap, effective, does a really good job. It's only when you start getting into more challenging schemes, like when you're looking at volts per hertz. Why is that a concern? Because if my transformer is trying to put up too much voltage for a low frequency, I can actually burn up the windings, even though the current's low. Too much magnetic energy, you can't get there from here. So it's other things that you're trying to protect against. And the distance schemes, like you can use current, but it's not nearly as reliable as looking at distance. And even distance is not as reliable as looking at differential schemes. So, any questions? Because this finishes up our module on fault current analysis. And then we have to do another hard topic, which is more math with symmetrical components, but we won't be doing any partial derivatives. That's just going to be living in a new domain. And this is the first time we'll actually be looking at unbalanced systems as we start to move next semester. Because we already talked about, next module, because we've already talked about the fact that most faults are single line to ground faults, which are unbalanced. So a lot of our work that we've been doing doesn't work for us anymore because our neutral is not at 0. And the other two phases, so we do per phase analysis, the other two phases don't have to be at the same magnitude offset by 120 degrees. So that'll be our next module. All right, any questions? All right, there's a homework assigned, right? Ready to go. So did everybody see that?
What did you do?
It's due in a week.
Okay.
Yeah.
And
It should be available now. Yes, sir.
Do we have lab next week?
Yes. Can't let you down, right? Good to see my smiling face. Although I do feel bad, like this is getting to the point in the semester. People are trying to get fatigued. Is that a reasonable thing to say? But getting close. Don't quit. Keep working hard. It's like slow and steady wins the race, right? All right, and not pontificating on life. I'll let you all go. Have a great day. I'll see some of you tomorrow. Be here tomorrow if anybody has questions. So take care, everyone.